And with that, I'd sort of like to tell you about some of this idea from my work, which is on capturing human behavior and language for interactive systems. So as we all know, computers are more and more integrated into society, into our lives, yet they still don't understand many of the basic human actions that surround them. So in this talk, I'd like to explore how we can teach computers to understand much more of this human context, and also what new kinds of interactions we can enable as a result. So, and if you think about it, this is really a key component of many of these core ideas we've had in human-computer interaction. For example, here's Mark Weiser, the founder of ubiquitous computing. And when Mark was first motivating this idea, he gives this example of a smart home that knows you might want to drink coffee after you wake up. Now, it's been decades since Mark first introduced this idea, but how close are we really to systems that understand these kinds of relationships today? For example, take an activity like packing. Now, personally, whenever I'm going on a trip, I always forget to bring my melatonin. So I would love to be able to tell a system, hey, when I'm packing, remind me to bring my melatonin. But for this to work, a system has to be able to really understand what packing is and be able to identify it. Similarly, there's many situations that are more the inverse of this. Situations, for example, where you don't want to be interrupted by text messages or other kinds of notifications. For example, if you're talking on the phone. Now, on the other hand, there are plenty of situations where this would be totally okay. For example, if you're sitting on the couch or taking your dog on a walk. And so sort of broadly, by understanding the kind of human context that surrounds us, interactive systems can start to make decisions that are more reasonable or not reasonable. Similarly, if we look at stuff in recent science fiction, or maybe the kind of stuff envisioned by Hollywood, again, we see systems that do things like play you upbeat music when you're sad, or warn you when you're leaving your home without your wallet. And these systems are all all understanding human behavior in a much broader sense than systems tend to do today. So today we have these systems that do a really good job of understanding facts about the world. We have these massively crowdsourced knowledge bases, systems like ConceptNet that can tell us relationships like water is a liquid. We also have these really great machine learning models, techniques like semantic parsing, which can learn from large data to answer questions like, who's the president after Barack Obama? But if we think about these motivating questions, things like understanding what happens after we wake up, or the fact that we're in a meeting maybe means we're busy and so we want to ignore a phone call, systems just don't tend to capture these kinds of relationships today. So what I'd like to suggest in this talk is that to really make progress on these visions proposed by Weiser and others, what we need are systems that much more deeply understand people, systems that really capture the breadth of human experience. So just to make this design goal a bit more explicit, what I'm really talking about here are systems that capture an enormous number of human activities. So there are thousands of activities that occur in daily life, things like waking up, drinking coffee, using a computer, going running. Imagine anything you do in a course of a day. We want systems that understand each of those things. And it's important to note here that this is kind of broadening out the reach of existing work, for example, in context-aware computing, where people do a good job of modeling a handful of activities. Or similarly, work that looks at modeling a large number of activities, but within a narrow domain. For example, modeling sequences of commands in Photoshop to predict what kind of command someone might want to execute next. So we want to sort of expand these ideas to encompass the full breadth of human life. Now, the obvious challenge you run into here, though, is where does this information come from? How do we capture these thousands of human behaviors and the relationships between them? And then how do we model those for use in interactive systems? So let's call that first challenge the sort of system model, and let's even say we can make progress on that challenge. There's still a second challenge I want to motivate today. And to do this, I'd like to sort of step back and sort of give a bigger picture of how users interact with systems. So you have a system, and you have an API or a kind of interface that that system presents. But just as critically, you have this idea of a user model, or how a user conceptualizes interactions with a system. And what's really important here is that when there's a mismatch between how a user understands a system and how a system actually works, you can often run into these big problems. So it's not just enough to be able to capture and model this kind of information. We also have to focus on how people can use it and how we can make these models interpretable to the users and system designers who might want to make use of them. So in the second part of the talk, I'm going to explore this more through how we can allow computational social scientists, this particular subgroup of users, to apply these kinds of models to enable new kinds of text analysis. So that brings me to the outline of the talk. In the first part of the talk, I'll sort of talk about the system Augur, which mines these thousands of behaviors in human life, the relationships between these behaviors, and exposes them to interactive systems. And then in the second part of the talk, I'll focus on more how people can use and interpret these models, and in particular, how computational social scientists can use these models to enable new kinds of text analysis. So with that, let's move into Augur. And sort of just to provide a kind of baseline for the kinds of predictions we want to make here, here's an example of a piece of context that an interactive system might want to act upon. For example, Facebook. It might benefit from knowing that if you're around Facebook, you might do something like getting a message or opening or closing your laptop. Similarly, if you're around, if it knows you're taking a shower, maybe it can then predict that you want to change your clothes or brush your teeth. Or if you've just ordered coffee, maybe it should be able to predict that maybe you're going to take a sip of the coffee or you're going to pay for the coffee. Or if you're around a stove, a pot, and a spoon, maybe you're going to do something like cook or stir the pot. So these are kind of baseline of the kind of information we want to capture in the system. But again, we're left with this question, which is just, how do we actually capture this information? We can't just sort of manually sit down and encode these thousands of behaviors into the system, much less the interactions between them. So we need some kind of data from which we can mine these things. But what does that data actually look like? Well, what you might want, or probably don't want, is this sort of dystopian world where cameras are monitoring everyone 24/7. You can trace all these user activities, right? Well, not a data set we have, also probably not a data set we want. Alternatively, you could look at stuff like social media, a different kind of dystopia sometimes. People post things there all the time, things like I'm running a marathon, I'm getting into a new relationship. But these things just don't quite occur at quite the right level of abstraction. So for example, people don't post things like, I'm typing on my keyboard, then I'm standing up, then I'm walking to my window. Right? We don't get this sort of prosaic or mundane information about the glue of human life. So really the fundamental idea in this work is, what if we use fiction to model this idea of human behavior? What if we use fiction to capture these many relationships between human activities and the context that surrounds them? So fiction has these really two great advantages. First, it's built on narrative. So characters do things to interact in the world, and there's a particular ordering or association of these things that they do. And the second advantage is that it has this really rich set of scene context. So there are many places, objects, even adjectives that surround characters when they're taking certain kinds of actions. And we can kind of combine this together to build these broad models of human life. So we want to use fiction, but what specific data are we actually interested in here? Well, the data we used was the specific data from the Wattpad writing community. And the main property of this data is that it's modern fiction. So these are stories set in the modern world. They're not sort of like in fantasy places on spaceships, right? We want to be able to model things that people are doing in the world. So we want sort of fiction set in the present day. And similarly, this is a very large corpus, more than 2 billion words. And as you can imagine, when you want to do this sort of broad data mining, a lot of data helps you quite a lot here. So just to kind of motivate how this technique might work, I'm going to give you a simple sentence. So he walked to the bookshelf, picked up his favorite book, and started to read. And even in this simple sentence, we can start to see how you can build associations between activities. So for example, picking up a book is perhaps associated with reading. And similarly, we can see how context terms are surrounded by these activities. So perhaps around a bookshelf, you're going to do things like picking up a book or reading. And so we can combine this insight together to create what's called the Augur knowledge base. So the first thing in here is obviously this idea of human activities. So what do we mean by this? Well, literally a thing that a person does. So a verb phrase with a human subject. So we can extract these things through subject-verb-object parses, drop articles and modifiers, lemmatize these things to collapse the vocabulary, and we end up with more than 50,000 of them, things like opening a refrigerator or turning off the lights or going to the gym. And then the second thing in the knowledge base is this idea of context, or this idea of objects, locations, and adjectives that surround characters when they're taking certain kinds of actions. So here we have more than 10,000 of these in the knowledge base as well. These are things like beaches, shirts, cars, or houses. And so we put these two things together to enable these two main APIs. The first is an API that takes a set of scene context and predicts an activity. So for example, given context like plate, fork, and table, I might predict an activity like eating. And the second thing is an API that takes one activity or a set of activities and then predicts an associated activity. So for example, associated with ordering and eating, we might have an activity like paying. So that's how the knowledge base looks, but how do we actually get here? How do we actually model the fiction to create these kinds of APIs? Well, so here's the pipeline. What happens is we start with the fiction, we run it through the parsing step, so we extract these subject-verb-object parses, these pieces of context. We then pass these to a neural network where the idea is we're trying to predict relationships between words in a sliding window, and I'll say more about that in a bit. We can use this neural network to then build a vector space, which gives us a representation of these high-level activities as well as the context terms, and then we can query that vector space to enable the two APIs that I just talked about. So this neural network, what is this thing actually doing? Well, again, the high-level idea here is we want to predict words within a sliding window to build a representation of activities and the context words. So effectively, by having neural networks make these predictions, we build up a sort of meaning or representation in the hidden layer of the network that provides a vector space representation. So if you've seen models like the continuous skipgram model, more commonly known as word2vec, this is a very similar idea, but we're extending this to operate on the high-level idea of activities as well as the low-level idea of words or context. So just to be very concrete about how this works, here's a set of sequence data and the kind of prediction tasks that we give to the network. So we have a window, it slides over the data. We have a target word, for example, here cold, and then we try to predict other words or activities within the window, things like day and walk home. And then we slide the window down, create a new target word. Now our target is day, and we predict cold, walk home, and eat lunch. We slide it down again. We make these thousands, even millions of predictions all over the data to build up this sort of hidden layer of representation. And again, the high-level idea here is we're building up a representation of these activities and contexts that we can then use for these downstream queries. So here's concretely what the network looks like. Again, it's probably familiar to you if you've seen these kinds of networks before. Again, what we're doing here is we're extending the input vocabulary to contain the high-level activities as well as the context words. Again, then that's passed to the hidden layer. We make these predictions about other words in the space, and then we sort of build up a meaning over time. And so what we can do then is take this meaning that we've built up in the hidden layer and convert that into a representation for everything in the vocabulary. So effectively, we have a matrix here where we can index in on that matrix to get a representation for different words and activities in the space. So for example, an activity like eat home or eat food would then have a vector representation that we could use for these downstream tasks. And so a vector space is useful here because it provides this sort of natural sense of similarity or relationship between different things in the space. So for example, if I have a vector space, then I inject a piece of context like lunch, I can just look in that space and see what kinds of activities are closer in the space and what activities are further away. So for example, activities like eating and cooking might be closer in the space, whereas activities like hailing a cab or driving are further away in the space. And we can formalize this through measures like cosine similarity, distance measures over vectors, which give you things like table and eating has relatively high cosine similarity, table and pet dog would have relatively lower cosine similarity. And the other nice property here is that we can query on multiple examples through this nice property of vector addition, right? So if we want to combine multiple pieces of context for a query, we just sum those vectors together, run that against all the other activities in the space using cosine similarity, and then can compute a ranked list of the associated activities. So this gives us stuff like this. If we're around a plate, a steak, and a fork, we can make predictions like maybe we're filling the plate or we're eating food. If we're around a bench, maybe we're making predictions like sitting. If we're around, or if we give an activity like waking up, maybe we want breakfast or we want to check the clock. If we're taking a selfie, maybe we want to take or upload a photo. So that's the kind of prediction that we can enable through this system. But what kinds of applications can we actually build on top of those models? So I mentioned earlier in the talk this idea of sort of a phone that's reacting to the context around you. So can Augur do something like this? Well, we can take an activity like getCall and look at the answer set returned by the vector space. We see things like answering call, calling back, ignoring the call. And now we can start to combine this with other kinds of context and see how these sort of relationships change. So when we add in something like cursing to this vector, we now see that ignore call moves higher in the list than answer call. We also see new things enter the list, things like throwing phone, which reflects the dramatic bias of fiction, which I'll say a little bit more about in a second, but also are in their own right useful things that interactive systems might be able to leverage. Similarly, at the beginning, I gave this example of packing, right? So can Augur do something like this? Well, given context like, for example, a shirt, shoes, and a suitcase, we can look at sort of what are associated activities in the space, and we see things, yes, in fact, like packing, also like wearing clothes or putting on shoes. So again, we didn't have to sort of manually predefine all of the different things that might lead to packing. The sort of natural relationships that fall out of this vector space sort of give us that information for free. Again, maybe there's another example where I've been spending too much money recently and I want a notification, a sort of text message, whenever Augur thinks I'm going to spend more money, sort of to prevent me from doing this. So there's a number of activities that might result in a future activity or an associated activity of spending money. For example, entering the store, perhaps you're likely to pay for something. But it's really quite a diverse set of activities here. So for example, when you enter or call a taxi, this is also an activity that's likely to result in a pay action. And again, we didn't have to sort of pre-encode all of these different activities that might be associated with paying. We sort of get these out of the relationships in the space. Okay, so that's a kind of illustration of what kinds of applications we can build, but how do we actually embed this system into the world, right? How do we actually get this signal about sort of, what are these pieces of context that surround us? So to do this, we can add a new layer to the pipeline, a sort of computer vision layer, taking off-the-shelf computer vision, processing some images to produce context terms, then pass those terms to the API to make these activity predictions, which then these interactive systems can begin to react to. So the basic way this works is you have a picture, you take some CV context out of the picture. So here computer vision tells us like this picture has people, mountain, tree, and backpack. We can then pass these to the Augur API and we see things like hiking or reaching the top. Or another picture, a beach scene. We can pass this to Augur and we see things like laying a towel or diving. And we actually built this out into what we call the dynamic music player. So we took a Google Glass, sort of had it take continuous pictures over the scene, had those pictures passed to the Augur API, identified sort of activities that it could, and then passed those back to play different kinds of music. So we were looking at 7 activities in particular, walking, working, sitting, eating, driving, buying, and reading. And we just sort of wanted to see, how well could the system do in practice at identifying this sort of basic set of activities, given the context that we were able to get from these images. And so just to give you a few examples of the frames here, here's a picture in the car, right? So of course we can predict that we're driving. And here's a picture in the library. And of course we can predict that we are reading. And so we computed precision and recall across all the activities in the system over these frames. And so what we found was that recall tended to be quite a bit higher than precision. So the system was relatively good at identifying an activity when it was happening, but there were quite a few more false positives, right, which lower the precision a little bit. So what this sort of suggests is that when you're designing for these kinds of applications, you should be focused on more recall-oriented systems, or at least systems that can tolerate this low precision. So for example, if I'm building a food diary that takes a picture automatically when it thinks I'm eating, a false positive there isn't going to be the end of the world. On the other hand, if I'm having a self-driving car react to some positive prediction, that could be a very big deal, right? So these are the kind of design constraints to be keeping in mind here. So sort of stepping back a bit, what I want to sort of really get across here is that this is opening a new design space which gives you these sort of 2 main abilities. The first is the ability to react to current activities, right? So this is expressed through things like, well, if I'm eating food, I want you to take a picture from my food diary. Or combining different sort of present signals, things like, oh, if I'm getting a call and then I'm cursing, maybe we're going to silence the phone. Or if I'm cooking, bringing up a recipe application. And then the second thing we get here is this idea of proactivity on future or associated activities. So for example, if I'm calling a suitcase, an Augur can say that, well, getting a suitcase is something that's likely to follow that. And then we have another piece of signal that says the suitcase is not with me. Maybe we can say, oh, you don't have your suitcase, give you a warning about that. Or if I'm entering a store, maybe we can predict that I'm going to pay for something, and so send me a text message that gives me my bank balance information. Or if I'm buying food, maybe we can predict that I'm going to cook later, and so sort of remind me what ingredients that I need. Right, so we sort of open up these 2 broad design spaces here. So with that, I'd like to move a little bit into more of a formal technical evaluation, because with these kinds of systems, you can sort of evaluate and see how these applications work, but it's also important to have benchmarks that you can use to continue to improve these models. Those are benchmarks that other people can use to build similar models and improve on what you're doing. So in this case, what we're going to do is crowdsource a sort of gold standard set of labels, basically replicating the kinds of tasks we're asking the system to do in practice. So here, for example, giving crowd workers a set of context terms, and then asking them to predict what kinds of activities will occur around those terms. And we can do the same thing for giving the crowd workers activities, and then asking them to tell you what activities are going to be associated with those activities. And so what we get here is a sort of data set that looks something like this. Here's a few examples. If you give a crowd something like clock, countdown, and television, they'll tell you, well, things like watching TV or celebrating or checking the time. Those are the kinds of things that will happen. Or if you ask the crowd what happens with opening a folder and reading a paper, they'll say, oh, maybe closing the folder or organizing or starting work. And now that we have this sort of ground truth data set, we can go through and actually see how well does the model do at distinguishing these things from the other stuff in the space. So we can compute some numbers here using AUC or AUROC. The nice thing about this is that sort of aggregates over all the different true positive rates. We have a baseline rate of 50%. So if the model's not doing anything, it's going to be a 50%. We also included a sort of baseline naive model based on co-occurrence accounts. So what happens if you just sort of take activity context relationships and build a sort of naive vector space using co-occurrence statistics. You can see that does a little bit better than the random model, but not as good as the neural network. you can also see that sort of as we increase the size of the hidden layer in the neural network, the performance goes up, but it sort of asymptotes over time. And I think it's important to point out here that while these numbers look relatively good, they don't represent performance on a real-world task. These are simply benchmarks that you can use to sort of evaluate and continue to improve the models here. So the second kind of formal evaluation we really wanted to do was attack this idea more directly of dramatic bias in fiction. Right? So in fiction, if I enter a room, it's perhaps far more likely I'm going to go and punch someone than it is in reality. Right? So to what extent is this a problem in our data, and sort of how can we start to evaluate this? So the basic idea we had was that, again, we can use crowdsourcing to construct a data set of a human prior over what's likely to happen around different kinds of contexts or different kinds of objects. So we can ask people effectively, if we have a chair, what is the likelihood that this set of activities is going to happen around a chair? Is it more likely that I'm going to sit in the chair, that I'm going to throw the chair, that I'm going to pull up the chair? Right? So we can sort of get this sort of distribution of likelihood over these related activities. And then what we can do is compare the distribution produced by the system to the distribution produced by the humans and sort of see what kinds of bias crop up. So when we do this in practice, we do see a significant difference between the system and the people. It wasn't quite as big as we were expecting. And actually, when we sort of dig into it a little bit, we see that the vast majority of this difference comes from these super mundane activities like seeing. So the system says you're far more likely to see a chair. So people see a chair in fiction all of the time. Whereas if you ask humans, are you more likely to see a chair or sit in a chair, they'll actually say you're more likely to sit in a chair. Right? So there's sort of an ambiguity here, or perhaps a human bias that's kind of affecting this a little bit as well. Of course, we did also see some of this dramatic bias that we were expecting. And in here, it sort of took more often the romantic turn. So again, because this is modern fiction, sort of set in the modern world, and we filtered for that, a lot of these stories were romance stories. Right? So if you have these kinds of interpersonal interactions, these are far more likely to result in things like kissing than you might have in the real world. OK, so with that, I really just hope I've sort of convinced you that fiction really can teach computers the surprisingly broad and accurate models of the world. Right? So these models aren't necessarily going to be driving your self-driving car tomorrow, but they do provide useful priors that we can use to start building new kinds of interactive systems. And so with that, I'd like to move into the second part of my talk. So in this part of the talk, I'm going to focus a little bit more on this idea of interpretability or usability of these models and how other kinds of groups can use and introspect them. And in particular, how we can use similar kinds of models to allow computational social scientists to do new kinds of text analysis. And this is a system called Empath. So as I've kind of just been talking about, today we have all of these really powerful language models. We have these word embeddings that give you this really rich idea of connotation. We have these great supervised learning models, things like convolutional neural networks, recurrent neural networks. We have this great unsupervised topic modeling. And then sort of on the other side of the world, we have all this stuff that's going on in computational social science. So people are doing things like tracking the spread of emotions on Facebook, looking at sort of what words indicate I'm lying or telling the truth, even trying to figure out what words indicate that I'm going to betray you. And if you think about it, you might expect that people are often leveraging these powerful language models to engage in this kind of work. But if you go out and look in this space, I think you'll find that this is surprisingly often not the case. And the reason I'd like to give in this talk for this is that computational social scientists strongly value interpretability in their models. Right? So when they report an effect, they want to be able to very specifically point to where did that effect come from. And so what this means is that people very often use what are called rule-based models, models that have a small number of very easily interpretable rules. So things like decision trees or inclusion-exclusion properties for words. And again, the goal here is that people are able to inspect these models with very limited technical sophistication. So a very common kind of model that people use here is what's called a lexicon, a category that sort of is represented by a list of words. So for example, if I want to measure anger in text, I have this word list, contains words like scream, war, mad, and so on. And I sort of use that word list to analyze the text across the category that I'm interested in. So there have been many of these tools created over the years, very extensively validated. Probably the most popular of which is called LIWC, Linguistic Inquiry and Word Count. This thing's been used for hundreds or thousands of studies, been very impactful. And again, how these things work is you have a piece of text, you walk over the text, you count the words that fall into the given category that you're interested in. You can then take normalized counts over those categories and then compare those counts across populations of documents to compute some kind of statistic. So if you just sort of think about this, you start to run into some obvious questions, right? So the first question is, well, what about breadth, right? What if I want to analyze a category that doesn't exist in any lexicon today? For example, a category like violence or like social media, right? These are things that don't exist in Luke. Similarly, what about words that don't exist in these categories, right? So these categories are updated very infrequently, once every few years or so. And so you end up with words like Bitcoin not appearing in Luke's money category, for example. So the idea that we're presenting in this work is that we'd like to take this very powerful and useful conceptual model provided by lexicons that computational social scientists use today and combine this with the power of these more sophisticated language models, right, and sort of get the best of both of these techniques. So what we did was we came up with a tool called Empath. And what this tool allows you to do is generate new categories from a set of seed words. So for example, if I want to analyze a category called social media, I can choose two seed words that sort of best approximate that category, words like, for example, Twitter and Facebook. I can then use Empath to generate a set of words, basically a word list that I can use to analyze that category, and then go and apply that category to the text. And again, we can use the sort of standard ideas from cosine similarity and other kinds of natural language processing to create these kinds of word lists. And what we can also do, because it's so easy to generate these things, is create a much broader set of hundreds of predefined categories that people can use for their analyses today. So these are categories like technology, violence, government, strength, all of these things that don't exist in lexicons like Luke. And again, the idea here is that we want to maintain interpretability while increasing the breadth in terms of the number of categories that people are able to analyze, as well as the flexibility, basically allowing people to generate these new categories on demand. Now, the question you run into, though, is, well, how well do these language models actually replicate these psychometrically validated word lists? Right? In some cases, literally teams of psychologists sat down in a room and created these word lists. So how well can these machine-generated lexicons actually perform in comparison to these things? Well, the first thing you want to do in this case is kind of create a baseline or a benchmark. And so what you can do is you can take correlations between the signals reported by existing similar human-generated lexicons. So I've already talked about Luke. There's other lexicons like the General Inquirer and like Emolex. We can compare the signals reported by similar categories in each of these tools and get Pearson correlations. And what we end up with is stuff like 0.89, 0.87. And now what we can do is generate our machine-generated lexicons and see how well those compare in comparison. So here the actual process is you have a set of training text. You choose some words on that training text that best approximate the category you're interested in. Then you apply that category on the held out test text. And then you compute a Pearson correlation over all these counts that you produce. And so what we end up with here is that we have a correlation on average of 0.9 over the categories we compared against with Luke. And this compares very favorably against the sort of Pearson correlations taken between the existing human-generated lexicons. So we can actually even push this one step further and look at, can we actually replicate some existing high-impact work in this space? So for example, in 2011, Golder and Macy published this study looking at mood on Twitter over time of day. And so what they found was, sort of as the day goes on, you have this sort of increase in negative affect on Twitter, whereas you have this sort of peak and decline of the positive affect. And so what we're able to do is sort of replicate those signals using the Luke tool and then show how the categories in Empath also replicate nearly exactly the same signals, again with this sort of very high correlation. And so the take-home point here is that really these unsupervised language models really can capture many of the same signals as these psychometrically validated word lists. Right? These models capture many of the dimensions that humans are using when they construct these word lists in the first place. So I mentioned that Empath has a number of other predefined categories. So how do we actually get these things? Well, the basic idea was we bootstrap them off of relationships in existing knowledge bases. So I mentioned ConceptNet earlier in the talk. This thing contains element of relationships, like shirts and hats are elements of clothing. We can effectively look at those relationships and use them to bootstrap a new set of categories in Empath. And so what we end up with is pretty large set of categories, things like journalism, envy, music, communication, programming, even stuff like hipster. And here's what some of these look like. So for violence, you have injure, fight, bleed, hipster, iconic, stylish, retro, technology, robot, browser, binary. Pretty diverse set of stuff. And so what we did was we took this and we sort of put it out in various different ways. We have a website where people can go and generate new categories to use for their text analysis. We also have a Python tool that people can download and use to either generate new categories or analyze text. And this has been picked up and used by a number of external researchers. So people have used it, for example, to characterize hateful speech on Twitter, to look at linguistic trends as communities grow over time, or even to look at linguistic differences between effective and non-effective team structures. And this work has been published in pretty respectable venues like ICWSM or CHI. Or sorry, is it Kai? Yeah, Kai. Also, it's in use by Facebook Data Science. So now actually what I want to do is show you how you can use this tool to extend some existing work in computational social science. So I'm actually going to kill two birds with one stone here and show you this demo through another tool that I've just published in Kai 2018 called Iris. This is a conversational agent that allows you to do data science, basically sort of mixed conversation and programming interface. And the main purpose for this is that it gives me a very quick way to go through this analysis and sort of show you the core of what Empath is doing. So the first thing I'm going to do is load up some data into the system. So you can see I start typing a command into the system. I get some query responses back. The thing on the far left is the thing that's actually going to execute. So now I'm going to choose a file. And again, the file I'm looking at here is some original data collected by Odd et al. And what they were looking at was some TripAdvisor data, some hotel review data. And what they were trying to do was distinguish between this and fake reviews. So they crowdsourced a bunch of fake reviews on Mechanical Turk, and then they looked for linguistic signals that would differentiate these real reviews from the fake reviews. So here you can see the data set has a review column. This is the text. It has a truth value. 0 is true. It has a sentiment, which we're not going to use. So the first thing I want to do here is just sort of show you kind of the breadth of the kinds of signals that Empath can capture. So I'm just going to type in Empath. So we're going to analyze the hotel data frame for Empath. It's going to ask me what column I want to analyze. I'm going to click on the review column. It's going to ask me if I want to aggregate the counts. In this case, yes. I just sort of want to overall count. And so I get these categories coming back. But what I think we can do better here, I'm going to actually just plot these things to give you a better sense of it. So I referenced the previous thing that we just did with that keyword. Now I'm going to choose a column with the labels and with values. And we'll look at just 20 categories. So here you can see things like vacation, traveling, tourism, things like air travel, business. Right? This is more or less the kind of stuff you'd expect in a hotel review data set. So the original work was really able to quite successfully distinguish the truthful reviews from the fake reviews. But something they weren't actually able to do was test this hypothesis from the other psychology literature that they had some evidence for. This was this idea that liars use less concrete or spatial language. So what we can do is actually generate a new Empath category to capture that dimension of language and then analyze these reviews to see whether we can pull up any signal from that category. So here I'm going to generate a new Empath category. And I'm just going to call it shape size, since that's kind of what we're going for. And I want these sort of concrete spatial terms. So I'm going to enter a few here. So big, small, and circular, these kind of describe shape, orientation of things in a room. I'd actually like to make this interactive. Would anyone like to suggest a new term so we can do some actual novel replication?
Long.
Long?
Dirty.
OK. That's just a sample of the kinds of things it gets. OK. Interesting. Very interesting. We'll see if that one replicates. We'll see if that replicates. OK, so now what we're going to do is apply this to the data frame. So what I'm doing is applying this category to the data frame. This time we do not want to aggregate the counts. So you can see now we have these new counts for each of the documents here. Now I'm going to sort of combine this with the existing data frame that we have. So I want to combine the columns. Again, I'm going to use the that keyword. And so now at the end here, you can see we've just appended the shape size on. And so now what we want to do is break these into the two populations, the fake reviews and the real reviews. So I'm going to do a filter operation. But first, I'm going to save the data. And so I want to filter the data. I want to filter by the truth column. I want that column to be equal to 0. So you can see we selected those. So I'll save that. Then I'll do that again. And you can see we have now the truth 1. Okay, so now we have these two populations, and we just want to do a t-test over the statistics we've already collected. So here, let's just type in t-test. Let's just do a student's t-test just for simplicity. And we're going to compare the truthful reviews. And again, select the shape size column there. And we're going to look at the fake reviews in comparison. And so, yes, even in that case, we still do get a significant result where the truthful reviews do have more of this concrete and spatial language. So we've actually done some new computational social science. Okay. So now I'd just sort of like to take a step back and kind of go over a few other research areas that I'm involved in and what some interesting questions here are going forwards. So I just talked to you about these two systems. The first, Augur, sort of mines these thousands of human activities, the relationships between them, exposes that data to interactive systems. The second system, Empath, is sort of looking at more from the standpoint of usability and interpretability, how people can leverage these models for new kinds of text analysis. But these systems really represent a subset of a much broader areas of work that, much broader set of areas that I do work in. Areas like computational social science, for example. So not only can we build systems like Empath to enable this kind of work, we can actually do some of this work, for example, looking at signals of gender bias in social media. Similarly, in the space of data mining, we can apply techniques similar to the kind of technique we applied with Augur to other domains. For example, the domain of open source code, looking at patterns there. And on the area of programming, again, through interfaces like the Iris demo that I just showed you, we can think about what are some fundamentally new ways that we can engage with programming languages. So I just want to step through a few of these areas now and kind of hint at what I think some important questions are going forward. So in this area of computational social science, much of my work has focused on this idea of sort of finding signal in text. So we've done work, for example, like measuring the trends in public perception of AI over the decades. This was work with Eric Horvitz, who, by the way, is joining us remotely. You can't see him, but he's here on Skype. Also, similarly, looking at signals and gender bias in social media, basically trying to understand when this happens, who's responsible for it, why it happens. And similarly, looking at signals of sort of dogmatism or this idea of polarized opinion or argument in social media. For example, signals of this kind of opinion on Reddit. And so just to give you an example of how some of this stuff works, here's a graph from the Trends in the Public Perception of AI paper. So you can see that in 2009, we just had this huge uplift in discussion around AI. On the y-axis here, we have this sort of percentage of all articles in the news that are discussing AI. But really, the main point of this work was to engage with a much more nuanced set of signals and look at how these signals tracked over the decades. So for example, this idea of ethical concerns for AI, or that AI is going to be making decisions for us that we might be concerned about, this is an idea that's been sort of increasing in the public consciousness in recent years. Or similarly, this idea of losing control of AI, like maybe you've heard of Elon Musk, this idea of summoning the demon, right, that we're going to lose control of these technologies. This is also an idea that's been sort of increasing in recent years. Whereas this idea that's more like the utopian economic vision, that AI is going to have this great impact on our work lives, this is something that's been more stagnant to potentially decreasing over time. And again, the high-level idea here is that as practitioners, it's good to be aware of these signals and how the public is viewing our work. And sort of in the worst case, you can sort of hopefully avoid things like AI winters. And sort of stepping back more broadly from this, I think it kind of illustrates a bigger question, which is just how we can learn from these large communities to make better decisions, potentially as a society to drive public policy, but also to build new kinds of interfaces. So for example, if we can detect signals like gender bias in an online community, can we start to use those kinds of tools to build interfaces that start to shape how that signal flows in the online community? Basically, can we start to build interfaces that shape these communities in the way that we want them to be? Now, the next area I want to talk about is shifting gears a bit towards more this idea of programming tools and how we can empower people to do new kinds of work and to better leverage programming languages. So in this area, I've drawn a lot on the same kinds of data mining I've just showed you in Augur. For example, in Codex, looking at statistical patterns in large data sets of open source code, basically finding code commonality patterns that might indicate a bug, or even finding patterns and then sort of farming those out to expert crowd workers to enable this idea of automatic documentation. We can kind of shift that idea a little bit to dynamic runtime traces through projects like Meta, basically trying to imagine what happens when a programming language is inspecting and aware of everything a user is doing with it, or everything every user is doing with it, basically tracking runtime data through functions, allowing you to do things like, for example, say, hey, you're using a function that's very similar to this other function someone else is using, but his function is better. Or even, in a more advanced case, when your function fails, hot swapping it in with a different function made by someone else in the community to enable this idea of automatic runtime patching. And similarly, as I showed you with Iris, this idea of, how can we think about new ways of interacting with programming languages? So I just wanted to spend a little bit more time on Iris. And again, as you saw in the demo, that Iris is a conversational agent that enables this sort of complex data analysis. But it's really driven by these two high-level ideas. The first is this idea from sociolinguistic theory of conversation analysis that looks at how humans communicate through back and forth conversation to express complex ideas. And then connecting that with a programming model, right? These programming models that enable so much of the kind of complex analysis that we want to do today. And making these things basically enable these open-ended command combinations that effectively allow users to build up ASTs over time as a representation of the conversation state. So here I think there's quite a lot of more work to do on this broader idea of tightening feedback loops between users and programming languages. So for example, once more users and data are flowing through Iris, can we leverage something like reinforcement learning to give much more sophisticated guidance as people are working through these tasks? Similarly, can we take techniques like programming by example to re-encapsulate a set of steps that one user just executed as a new standalone function that someone else in the community can use and benefit from? So there's quite a lot of future work to go on here. Now there's one final area that I want to talk about, which is kind of drawing on this similar idea of a user model, but with more of a focus on what we can think of as decentralized systems. So if you go out and sort of look at how users are interacting with decentralized systems today, for example, blockchain applications, talk to people in this space, most users have absolutely no idea what's going on underneath the hood of these applications. Their mental models are just not designed for how these applications actually work. Similarly, if you talk to programmers, there's a huge set of skills that they need to understand to be able to program and develop these applications. Skills like understanding how a signal sort of propagates through a distributed network, or the various constraints provided, again, if we're talking about blockchain applications, of smart contracts, right? Or public key cryptography, huge set of things here. And there's a big opportunity to provide abstractions in DSLs that sort of bridge this sort of abstraction or this gap for these programmers who don't necessarily understand these ideas. So much of the work I've done in this space so far has actually focused more on community development. So with others, I co-founded this organization called COZ, a decentralized open source community that is building these blockchain applications. And so we've actually had quite a lot of success here, developing applications with collectively hundreds of thousands of users. And we did this through really making open calls to the open source community, which have resulted in thousands of contributions from hundreds of people across the world. These contributions have allowed us to do things like develop an asset management platform that is responsible for more than $10 million in transaction volume every day, or build a Python DSL for smart contracts that has created these smart contracts worth collectively hundreds of millions of dollars. So what I really want to point out here is that this sort of platform provides a huge set of data both about how users are interacting with these applications and also how programmers want to develop them that can be a huge resource in answering these kinds of research questions going forwards. So I'd just like to close on one final thought, which I think will have quite a lot of impact in the future. So hopefully over the course of this talk, I've convinced you that we can draw on community data to empower interfaces. But I think it's just as important, if not more important, to think about how we can close that loop and build interfaces that really empower communities. So one really important tool we have for this are these sophisticated machine learning models. But these things unfortunately require a lot of data. But I actually think this presents a big opportunity for us. So we're in the midst of an open source deployment of Iris in partnership with bioinformaticians at Stanford, others in data journalism. In the course of this deployment, we hope to collect data from thousands, tens of thousands, potentially even hundreds of thousands of users to better understand how people work through these data analysis pipelines. And so what I hope to achieve by this is this idea of a virtuous cycle, where an interface learns from a community, goes on to empower work in that community, learns from the community, and again goes on to empower work in that community. Effectively getting at this idea of tightening feedback loops between programmers, communities, and the programs that they write. So with that, I'd just like to thank the many mentors and collaborators that I've had over the years. In particular, my advisor, Michael Bernstein. It's been really, really great working with you. I'd also like to give a special thanks to my committee. So Eric, who's on Skype, Eric Horvitz, Sean Fulmer, James Landay, Manish, everyone, thank you so much for being here and for providing your advice. Also the many graduate students who really shaped my time here at Stanford, right? Like it wouldn't be the same without you, so thanks so much. And finally, the undergraduate mentees that I've had over the years, whose results have really helped shape some of the work that I presented today. So with that, I'd just like to thank everyone and open it up for discussion.